Hello, am I audible? Am I good? Okay. So welcome to lecture 4. Just for your information, I have already shared the detailed notes on Moodle. So I hope all of you are following Moodle. This is how the Moodle page looks like. So we are running notes from basics of ML to large language models. So I have not uploaded everything. I'm just putting a lot of figures in there. But yeah, to some extent, it's there here. Try to give examples, of course, related to Indian context. So yeah, hopefully you get started reading and I'll keep updating the notes. Like some of you had asked, so I pushed those notes. And maybe I'll refer to these notes as we progress to the class today as well. Okay, so with that note, let's get started with this lecture. We'll talk about, we'll conclude discrete optimization. I hope you have also attempted the homework problems. So every class I try and give homework. So hopefully seeing the homework problems. They're all kind of from Moodle. So here you see, sorry, homework derive the gradient and Hessian for the loss functions listed on last page 67. Did you all look at it? I also put it on Teams. Did you? Yeah. So please make sure you kind of look at homework problems in every class. Okay. And then we'll move on, of course, to optimization principles themselves. So for those who came late, we have uploaded a whole bunch of notes on Moodle. So this is what was pending: feature selection, data partitioning. Again, context of feature selection, I'll talk a little bit from my notes. The others are going to be a bit routine. You also hopefully brushed up from last class, from last year's lectures that I've posted. So as I said, discrete optimization is very ubiquitous. While people generally talk of continuous optimization, a large part of inference, any machine learning inference involves discrete optimization. The moment you say, find me the next prediction, you have to do some discrete optimization, right? And that's most practical. And as I said, continuous optimization is just a relaxation. So these are all of these, right? Natural language processing, we saw generation of parse trees as examples, syntactic parse trees, constant trees, genomics, computational biology, selecting peptides for proteins. Right? So all of these are discrete optimization, even predicting summaries, predicting tokens, predicting answers, you're predicting tokens. And while images speak 1,000 words, so we concluded last class with this image segmentation problem. And if you're looking at a problem, let's say, of finding correspondences between two images, the image on the left here, which is a tilted version of the image on the right, you basically are looking at correspondence of points. There's a bipartite matching problem. Now, interestingly, you could pose this problem as a max flow problem where you have associated capacities with each edge. The capacities reflect how strongly corresponding are the different patches across the two images, right? So if these two patches look very similar, the ones in black, you would basically say that the capacity associated with this pair will be high, right? And how does it help solve the problem? More the capacity, more is a flow that can go from this artificial source node to this artificial sink node. All this makes sense only when I have some constraints. So you are trying to maximize the flow going from the source S to the collection of nodes U in the left image, such that the incoming flow at every node P equals the total outgoing flow from that node P, right? And the Q's and the R's are all other incoming nodes from where the flow comes to P, and outgoing nodes where the flow goes from P, right? P from Q to P and from P to R. With another constraint that the flow on each edge should not exceed its capacity. Now I have also artificially put a capacity of 1 on each edge going from source to the left side image, and on each edge going from the right side image, or the pixel in the right side image, to the sink. Okay, so this is where we concluded. You can likewise also define the segmentation, right? You're trying to solve a segmentation problem where I'm trying to find the outline of this aeroplane with respect to its background. This also I can solve with respect to an existing known problem, a discrete optimization problem called the minimum cut problem. This was a max flow. This is a min cut. In fact, there is a relationship between max flow and min cut. What is the relationship? One can give you the other, right? Now, we just find it easy to solve the second one using a min cut. What is a cut here? Cut basically corresponds to identifying the outline of this image, the aeroplane image in this case. So you have a cut, you can see the small edge, right? Anyone wants me to zoom in? Is it clear? Is it visible? So you have a small edge going from one edge, any pixel to any other pixel, and specifically here the edge is shown between a pixel within the aeroplane to a pixel outside the aeroplane. And what we trying to encode in the pixel is what? What will we encode? So in the edge. And the more homogeneous a region is, more would be the similarity between pixels in that image, in that region. And therefore, what would you expect the edge to reflect? Could it be a cost? So here it was basically the similarity, right? C, the capacity of similarity here. C is cost. How much is the gradient? How much is the difference between those two pixels? So here you see that that's why deliberately I showed a pixel inside and pixel outside. You would see that there's a big difference. The gradient is high. For example, you could measure it as difference in simply the grayscale or RGB values. And what you're trying to do is identify a subset S from this image such that the sum of all the weights associated with edges within the image, within the S, should be as, how should it be? Should be maximized or minimized? Sorry? Is this correct or is there a mistake? So here we are looking at similarity from S to S complement, right? What would I like? I would like all the pixels within S to be as similar as possible, which means the dissimilarity should be low. Or the other way of putting it also is that maximize the dissimilarity between pixels within S and pixels outside S. So you please observe what is being shown here. Maybe I'll enlarge this. It's not visible. Okay, so what we are showing here, and I'll write it on the board as well. The notation U. UV in SS dash of CUV. I could also consider a subset of V such that summation of UV in S of CUV is minimized. This is another formulation. Is there any reason you would prefer the first one or the second one? One is to minimize the intra cost, right? Intra region cost. Yes. Mm-hmm. Mm-hmm. Okay, so we'll actually look at a more nuanced, a more advanced version of this entire exercise through the lens of building against a large language models. So imagine that I had to tokenize text, right? And this is very typical. So let me pull up from the notes again. This is from the notes. Okay, so this is one of the later chapters. You can go. Okay, so tokenization. So tokenization basically, let's say I have the word playground, right? I need to identify how to split words. Should it be play and ground? Should it be just PL and GR and OUND, right? There are multiple possibilities. Now, each of this gives you a very different representation of the document. And more so if you're looking at multiple languages, not just multiple languages, even say multiple accents or multiple variants of English, Singaporean English versus right, North American English versus South American English. So, so there are multiple tokenizers, byte pair encoding, word piece. Byte pair encoding is somewhat trivial. It just tries to keep merging words or pairs, which give you bytes, which give you highest frequency until a threshold is reached. myopic views, but they are effective. At least they have helped us scale models. I think that's important. Now, this is a big feature space, right? And what you want to do is basically also score. You're not only looking at these individual words, and let me give example here. Let's say unaffordable housing crisis, affordable, right? Let's say that is a simple sentence. Now you see that affordable has repeated twice, but of course, this is just part of a larger scheme of things, right? And therefore, you might find multiple other byte pairs which might have good frequency. So there are some simple merging steps being shown here based on frequencies. The most frequent pair is FF, then the most frequent pair is AF, and so on. Right? Affordable is repeated. And let's say this gives you, based on some corpus, these are the, as these to be the tokens, UN, AFFOR, DABLE, and so on, right? Now this is what BP tokenizer does. It's effective in reducing vocabulary, can also handle out of vocabulary words, right? Instead of saying affordable, if I say affordability, I want to be able to still handle, right? Or someone says non-affordable instead of unaffordable. Again, you don't want it to be treated as a foreign word altogether. But there are issues. There are multiple issues which other tokenizers try to resolve. For example, this word piece tokenization says, well, it's not sufficient to look at the frequency of X, Y alone. You should look at the relative frequency, right? How frequent is AFF, right? So I want to look at some scores. Look at this. This is just giving you a score of this is often used in your likelihood ratio test. How likely is XY relative to the likelihood of X and Y alone? If X and Y are very frequent, then it's natural that X comma Y will be very frequent, just by chance. So you want to see, well, is this co-occurrence a chance event or not, right? It's possible that there was actually some formatting error in the text, and as a result, HTML tags were removed and two words got merged. And very frequent words will give you some new mergers, right? Now, what we are discussing here is going beyond that. We are saying, well, given some random variables, think of these random variables here as the possible the features. In this case, could be just the token, right? You want a subset of those such that the subset is as good as the original set. That is what we are trying to do through byte pair encoding, right? I want to be able to recover the original set of words, the vocabulary. So I want this A, which is what I'm trying to identify through some scoring. So how do I come up with a score, a measure that is reflective of this goodness of being equivalent, right? Especially at scale. So yeah, I'll just replace this X with an A. What I meant is an A here. Okay, so one way is to maximize. So let's say I have some target, which is the label Y. So I'll say I'll maximize the mutual information. What I've shown is not very different from mutual information. Okay. However, in mutual information, you are measuring the information between the input features and target label. Here, I didn't have the target label. I could add a target label here as well, right? I'll say, well, not only how good the features are with respect to each other, but I could have a new score. So this is this, let's say X1, X2, instead of calling it Y. Now I could have a score of X1, X2, the feature set, and that is what I'm representing as XA, comma Y. This is the label. And some information theoretic measure. What do you think is mutual information? It is the, anyone wants to define mutual information? This is an example, of course. It has to do with entropy. Entropy, I will denote by H. Yes. Anyone wants to guess? It's in terms of entropy, some differences, right? Do you think it'll have some form like this? HXA minus HXA comma Y? That's entropy, H. H is entropy, which is including negative log. So I'm not writing the negative. Sorry? So I have to subtract something from this then, right? So you're saying, well, I want to look at the joint entropy, the joint uncertainty kind of thing, minus the uncertainty of each of those individually, right? Minus H of XA minus H of Y. This mutual entropy, mutual information. Okay, so this is one way, maximizes mutual information. This kind of measure. So you can think of it a more refined likelihood ratio, refined version of which is based on distribution, based on information theory, right? Now, it turns out that this mutual information function is very much like a concave function. Okay, yeah.
Use CA also to select the question. So that comes under continuous optimization. So why is there like this?
So very good question. How is it related to PCA? Well, PCA, right? If I had to do PCA on these word pieces, right? What would I do? I will actually consider a linear PCA will give me some linear combination, which may not be interpretable. Now, PCA might be good if I want to just classify a document. Okay, I'll say 0.5 times un plus 0.6 times durable. But if I want to reconstruct, and that is what, very good question, excellent question. Please ask such questions, right? The PCA has a limitation when you're trying to reconstruct text. When you're trying to reconstruct and decode, in the sense of a decoding, right? I can still reconstruct, but it's going to be through some intermediate space which may not be as interpretable. So eventually, once you have these word pieces, you pass it through some transformer architecture, which I've documented in my notes, and then you again are in the same word vector space. So yes, you have to use vector somewhere or the other, like PCA. Question is, how early do you want to do it? See, that is where, how early you want to relax discrete optimization to continuous optimization. The earlier you do, the more interpretability will be lost. But the earlier you do, the more computation you can save, the more you can scale. So scale versus meaningfulness, right? Scale versus efficiency versus effectiveness. These are actually very important questions. The more you switch to continuous optimization, you'll be efficient. But effectiveness is a question mark. You can persist with discrete optimization, do decision trees. You'll be very effective. You might be effective. Again, may not scale at all. Therefore, effectiveness on a very small sample is what you can show. Excellent question. I think these kind of questions should bother you, right? Right. So coming back, so I hope you got the point, right? The point is, this example, I'm now trying to identify a subset here, a subset of the x's, which would do well on a downstream task, let's say summarization task. This is a very large search space. Of course, people haven't solved this problem, but people have, for example, seen how well, and there's some recent paper, right, Pratik? There's a paper which actually studied how the tokenization is very strongly connected to mixing of the data that is used to train the models in the first place, right? Tokenization and data mixing, right? Because the subtokens, the subsets xi, xa that you identify are based on some data. I mean, in this example, when I compute these frequencies, the frequency is based on what? Frequency is based on some data, right? So if I give you, so instead of saying I'll subset features, I can also say I'll partition data first. Based on data, I'll identify the feature, I'll identify the frequencies and the corresponding subtokens. This is super important because, as you'll see, a lot of the optimization is based on stochastic processes. You create sub batches. You basically create partitions. You create, right? And in that process of creating these batches, your overall statistics and distributions can get messed up. Right. So there's a lot of interplay between the data and the features. Okay. But the good thing about some function like mutual information, though, right, coming back to the optimization formulation here, is that it actually is a kind of submodular function, which is a kind of concave function, concave-like function in a discrete space. So like concave functions have diminishing returns, they have exhibit a max. Similarly, the submodular functions also have this, the discrete functions with this diminishing returns property. This is clear? So I'm actually thinking this is one of the grandest problems, right? Doing very good tokenization of the text in a way that aligns very well with the data distribution and gives you interpretability without vectorizing too soon, right? Like PCA could vectorize very soon. Okay, so yeah, some part of it we have also been trying to address in our own work. We have tried to put things together in this. This mutual information, for example, is used as part of our targeted subset selection, right? But there's a lot that needs to be done in this space. Let's look at the other aspect. So far, I talked about feature subset selection, but there's also training data subset selection. The data based on which you're going to measure the frequency in the first place, right? The frequency I talked about here. What is this frequency based on? I mean, this is just a simple frequency, but you could look at more complex, as I said, this mutual information, a kind of information theoretic measures. So here the problem is the kind of the complementary problem. Given a training data set, which consists of instances x1, y1, x2, y2, x and yn, and you're given a budget k. What you want to do is identify a subset of the data such that a function that I use to measure on the subset gives me similar models, or models that are as effective as if they were trained on the entire data set. I think this is the key here. Okay, so you have the subset S. Sorry, this is subset Sk of the set S. I've used different notation here. And what I want is a function Fs to be approximated well by Fsk. Okay, I've given some possibilities here, right? Fs, for example, could be that function which minimizes the loss on the entire set S. Fsk could be the function that minimizes the loss on a subset, right? So what you're basically trying to say is, well, give me a function that, while getting similar losses, in the hope that the performances with these functions will be the same. We don't know the functions. So here you see, Fs is argument over a large class of functions based on the loss. So you're searching over functions, you know the form of the function. If your question was form of the function, I know, right? So there are two optimizations going on. This is another grand optimization problem, bi-level optimization. I have some functional forms. Let's say they're all, let's say transformers with 5 layers, right? And a feed-forward connection. Let's say I know the architecture. But the challenge is the parameters of the transformer model I want to learn in such a way that a loss is minimized. That's what in our hands is. Like we have taken logistic phase loss, cross entropy loss. I want to minimize the cross entropy loss such that the cross entropy loss yielded by a particular instantiation of the parameters on the entire data set, right? The function that is yielded because of that, and the function that you get based on a subset of the data set, the loss being minimized on a subset of the data set Fsk. These two functions behave similarly, and their behavior is, the similarity in behavior is measured through another performance. Now, it can turn out that the second performance is the same loss. That's also fine. So I can say, well, as a simple thing, I can say, give me the functions f such that the loss, but I can say this is a loss on validation set, based on argmin of S over argmin of the F on the complete set S. Okay, I'm deliberately avoiding parameters, but when you say argmin of F over S, you're saying the function that minimizes the loss on the training data set with respect to the entire subset S. So this is S is a train set, right? S is a train set, complete train set. Okay, this is the S outside. And what I'm trying to seek is the SK such that the loss, the same loss, okay, I can use the same white color here, so there's not a different loss. But this loss is measured. Okay, so yeah, argmin over the, let me just put theta here, okay. Argmin of theta along with SK, F of SK. So this is what I want. Oh, sorry, there's a mistake here. I have missed loss here. Okay, argmin of something, right? What is the argmin of what? So I'll just correct this. Argmin of loss. Yeah. So question was, are there any assumptions here, right? With respect to what I've written. Well, this loss is what is called performance on the board. The board have used a different keyword here. This loss is called performance. Right? Now, an example of the performance would be the same loss on validation set. So one assumption you could make, and we did in some of our papers, is we assume that the loss being measured is the same loss as this one, but on validation. This is on train and this is on validation. That's one kind of assumption you can make. Right? The other, there are more assumptions. You can say, well, one is a monotonic transformation of the other. Right? So monotone transformation and other assumptions. So some assumptions are often desirable. I mean, in general, you always make a monotone assumption. I mean, if you're measuring F score, then you would expect that your optimization is something that over a loss function that actually maximizes the F score. F measure, right? The harmonic mean of precision and recall.
Such that it is representing indirect things, then isn't it ensure that whatever question we take, it will give the same performance on the subset as compared to the entire data?
But it's a function of the loss. What loss am I using? So your question is it ensured that if I pick the SK that minimizes any loss for any functional form, it'll also give me the minimum performance on the minimum performance on the perf function, right? Not necessary. For example, right? If let's take the simple example, I'm trying to find a needle in a haystack, right? So let's say my loss function is based on how correctly I classify needle from haystack. So needle is just one in a big haystack, right? So if my training loss is just about whether I find an object to be correct or not, then I can actually be correct most of the times by saying everything is hay. Needle hi nahi hai. There's no needle. Why? Because most of it is hay. But if my performance is, did you find the needle? Yes or no, right? That's what a doctor would, or someone would be interested. Where is the needle? I say, I couldn't find the needle. Zero. So the performance measures can be very different from the loss measures. You understand? So the performance measures, for example, might be just precision of that particular class. And the loss is saying overall accuracy. The other considerations also. Well, you can say, well, if I don't want to minimize these, right? Let's say argument. I'm saying too much. Argument means the function that minimizes. But instead of that, I might also look at some intermediate losses, intermediate canonical representations of those points. That is what I've written there in green. Why not replace these minimizers with intermediate gradients? Intermediate gradients like gradients of, so you have a homework problem on computing gradients. So I can actually be computing gradients, and let's say I'm doing gradient descent. I want to make sure that the gradients of these two are matching without necessarily minimizing them, the losses. Okay, so there are multiple variants possible, but I think you've got a prelude into this kind of grand bi-level optimization problem, right? So this is the whole point, right? Select a subset of data points such that the model trained on the subset of data is as good as the entire data. But the notion of goodness is where I'm trying to bring out not only all the nuances, but also the criticality, right? If the two don't match each other, then you'll have a problem in what you're trying to solve or what you're trying to obtain. So this is a lot of data efficiency for efficient training. And this can make even more sense when the labels are missing. In fact, this makes super sense today when we're dealing with so much of self-supervised learning. Self-supervision means that you're just trying to predict next tokens, right? that is what I've also tried to present in the notes. That's the simplest problem of just trying to mask tokens, right? Do mask language modeling. I think. Sorry.
The optimal subset.
This SK? No, that it's not necessary. It may not be. In fact, solving the problem. So first of all, the function. So the loss function may not be convex. So we'll come to convexity. If the loss is convex, there's a good chance that SK is optimal. Right? But if the loss itself is not optimal, then so it's not convex. You can't comment. Most of the times you can't comment. So let me just give you an example of what GPT-2 does, right? GPT-2 was one of the simplest problems. So you have, typically you're looking at input output, right? In self-supervision, what you're looking at is predict the next word, right? You're predicting next word is sequence based on the preceding context. As simple as that. So you don't need label data to train GPT-2 model, right? So given this, and they actually trained it on a lot of web text, the details are the notes. So that's the reason this makes more sense when data labels are missing, right? And it's also possible to use this when you want to label data. Let's say I'm not dealing with self-supervision, but actually supervised setting. But I want to identify the subset A or SK that needs to be labeled, right? For example, if I'm trying to, I don't know what needles look like, but if you identify a subset of objects, maybe you'll identify a knife, a scissor, a pen, a pencil, and you'll ask me, well, can you label if this is a needle? That makes more sense. But if you start showing me all the hay in the world and say, please label this is a needle, I'll go mad, right? And in fact, labelers can make mistakes when you don't show them meaningful objects to label. The probability increases. So here you're saying, well, get me a subset of the points to label in the first place. Well, and this is where, again, see, gradients here are now with respect to the target object, for example, needle or not needle. So I'm trying to say whether a gradient with respect to XA is matching the gradient with respect to the entire set V. Now the gradient could be with respect to a particular objective, for example, classification as needle or not needle. Okay. Okay, so overall, what we are saying, I mean, this is all detail. This is basically the high level view, right? I want to maximize minus of D. The D is basically a distance, such as say KL divergence, right? I could also be minus D could also be information, mutual information between XA and XV. So now you're looking at a subset. See, earlier here we were only looking at a Y and an X. Now we have generalized the problem. We're saying, oh, I could have a subset of X, but I could also have a subset of Y, right? Or you know, a set of labels Y, and I want to kind of minimize that distance. In this case, it could also be just XA and XV, two sets, right? So all kinds of variants exist. Thing is, we have to put some constraint, because if you don't put a constraint, you might just get the entire ground set. Okay. So this is a cardinality constraint, but there are other constraints possible as well. And hopefully in your course, you deal with partition matroid constraints which deal with, what points you think should come. If you pick this, you should also pick the other point.
Of negative real divergence and
So did I say distance? I mean, basically, I'm saying max of similarity. You could also say max of S. That's also fine. Max of S is another way of writing. Or max of that fine? That's also possible. There's no specific reason. And the distance we brought in, just see, similarity typically requires you to have some kind of a dot product space, right? Distances may not require those. I mean, distances you could measure from what is probabilistic similarity? Probabilistic distances are easier to talk about, right? So from that perspective, KL divergence is a measure of distance. So similarity is required some kind of vector dot products. Yeah. You could also do that, yes. Okay. What did I do? Okay, so this is the basic thing. And then again, we've been doing work on this space, but of course, a lot needs to be done now, given the surge in self-supervised learning. But all this is work, grad math, Celcon, etc. Work we've been doing, at least in the supervised settings. Yeah.
So if we take a data set that is so wouldn't it change the score of the text? Because we are taking a subset, we want it to be helpful.
So your question is, if I take a data set which is a subset of original text, won't the scores change? Yes, the scores will change, right? In fact, the loss will change if the subset changes here, right on the board. But there are other properties of the loss. We are interested in now in this course, we are interested in properties, which will make the solution here, if not feasible, in polynomial time, at least there is some guarantee decrease at the least. Of course, that is at the least. But can I also put some bound on the distance between the gradients? The bound may not be an absolute bound, it may be very relative. Some way of characterizing how far these two losses are, right? And especially if for a discrete function f, right? The function f itself could so loss, some properties of loss, which are more on the continuous space, but also some properties of f. That is where submodularity could come in. Right. So I think good question, very good question. So properties of loss, for example, convexity or regions of convexity, and properties of f could be submodularity. Okay. Or different variants of submodularity, like weak submodularity. I'll conclude with this probably, one, not two last problems. The k-mu clustering problem. We have already dealt with clustering. Now, if you remember, I talked about the facility location problem, where I want to locate facilities which are in tangible regions, right? I don't want to build a warehouse in the middle of a river just because the river is exactly midpoint between two cities. I want to locate it in one of the cities. Yes, there's a compromise, but feasibility is important, right? So given a set of data points and a similarity function, so Sij between pairs of points, and I have a budget, which means I can't be, I can't be spending more than, selecting more than k points. For example, there's a budget on the number of warehouses, right? So the Sij is the distance between two pairs of points. For example, when I'm trying to locate a facility, these are the set of cities, where people, or set of locations where people are based. And I'm trying to identify 2 warehouses, places where warehouses should be set up. And as I said, I want these means to coincide, these points to coincide with some actual facility. Means may not coincide, right? K means may not coincide. So this is very closely related to the facility location problem, which I'm using to motivate this discussion. Okay. So the goal is identify the K bedoid. How do you do that? Is this problem clear? So I have to pose the optimization problem here again. Okay, so the optimization problem. Now what you're seeing is slightly, earlier we were talking about a mixture of discrete and continuous optimization. We are now back to only discrete. This is purely discrete. So what are we doing here? We are saying, well, and this could actually be useful when I'm trying to identify, let's say, across different domains, I want to identify some representative sample of documents, one for legal domain, some samples for legal domain, some samples for medical domain, right? To train some model. If you say, oh, find the mean, I mean, what is the mean of a legal and a medical document? It might be meaningless, right? So mean might be just meaningless. And that's why what I want to do is for this set of points and for this set of points, hypothetically, I'm trying to find for each point. So let's say Sij is a similarity of 2 pairs of points. So for each point I, I'll find, so this is say, this is Xi, which has similarity Sij with some other point J here. This is Xj. Okay, this is another Xj. This is Xj prime. Okay, so this is one distance or one similarity. Let's use similarity, not distance here. Okay, so this is one similarity. This is another notion of similarity. So you can clearly see this similarity is higher, right? So what we are saying is across all the J's, find the most similar point, which will give you this Xj. But that's not sufficient. I want to do this across all the I's, right? So I want to sum this across all the points I in A. All the points I. And I want to find an A, that a set of points A which contain those points J, such that it maximizes this overall similarity of each point I to the closest cluster or centroid or midoid in this case. So that's the whole point. A point I is assigned to the midoid J, which is most similar to it. Otherwise, if I have to just solve this by brute force, how complex will it be? I'll have to explore the power set, right? I have to look at 2 raised to n possible A's. Okay, of course. So I put a cardinality constraint. I said size of A should not be less than, should not exceed K. So of course, the similarities themselves can be chosen to be rich. I'm not saying the similarities should be just based on some original Ross feature representation. You could in fact use a model based similarity. You could use gradient similarity, right? If you're using this as part of some larger machine learning objective, you can say the SIJs are based on distances of gradients. Yes, this is also data subset. Yes, absolutely. This is also, there's a slightly more, so data subset selection, you were only looking, so earlier when I showed, you're saying, well, I'm trying to maximize some function. Here, I'm trying to not only find the subset S, but I have some more specific requirements. They should be a representative of other bunch of points, right? Yeah. So all these are related. Yes. So just different flavors of, one is a flavor of coverage, the other is a flavor of representativeness, right? One is feature coverage, the other is example representativeness. That's true. In fact, when we maybe hopefully we get the time, we'll talk about these different flavors. Okay. So yeah, we actually will see later on that this is called a facility location problem, and again, there's a submodular function. So you can go to the submodlib library, you'll see all the three classes of functions, which are representation based functions, diversity based functions, and coverage based functions. There are three classes of functions. Okay. Go to especially if you go to submodlib. So I'll just show you the GitHub page here, right? So there are the notebooks, etc. But also there's a very detailed read the docs, which you can. The read the docs will probably give you a lot more insight into the classes of functions. So it's the general functions, which are facility location, disparity bin, log determinant, blah blah blah. But there are also more refined functions like mutual information functions, which are based on the notion of mutual information between sets of conditional gain functions, conditional mutual information. So I didn't talk about these. Maybe later on we talk about these. You can also have conditional gain, which is looking more at distances rather than similarities. Okay, yeah. So you can basically run through any of these. Like what we were just now seeing is, okay, facility location, the raw facility location function. So each of these functions, facility location exists there, but it also has a mutual information version. And exactly this, and what are the functions that submodlib provides. There are many optimization algorithms implemented there and so on. Okay, so now coming back, we have now seen this big picture, some elements of all of this. I think you have now equipped to deal with your projects, right? And today is the deadline, right, Prateek? Or tomorrow. Any questions? I think we have given enough flavor. Algorithms we'll learn, but it's life is always like that. You don't have everything served before, right? So any questions for Prateek? I think there were some questions you had for the TAs, or you can ask at the end of the class also. He's available. Yes. Previous ones also. Previous ones also. Yes. Most of the time you put some constraint. The constraint may not be a size. Constraint can also be, as I said, some kind of partition matroid. I can say, well, I want to make sure that every element in this partition is covered. So I pick one from each partition, let's say. We will look at it later on, but if you just want a very quick preview of how the loss functions look like here, right? So you want to look, say, let's say at log determinant. So log determinant is basically log of, can you see this? Log of determinant of a submatrix. Let's say I have a bunch of points, V, from there I subset A. So this is a log of determinant of A. Or the similarity of points in A, sorry. L is a similarity, subsets of rows and columns indexed by the set A. So now what was your question? What was your question, sorry? Yeah, this is an example, another example loss function. And this is basically a log determinant. It's a probabilistic distribution. You'll find more. Graph cut. So graph cut basically looks, while we were looking at just max of sum of max, this is looking at sum minus, so max of one sum minus another sum. The first sum is basically looking at similarity between the subset and the entire set. The second component is looking at the dissimilarity, or kind of negating the self-similarity, the similarity within the set. So feel free to navigate this. Okay, I think we have also seen that there's some interesting properties. For example, these functions have concave properties, many of them, in terms of maximization, but they also have a convex-like property. We may not have time to see, but you may see through project. These have convex-like properties when it comes to minimization as well. That's very interesting. Whereas most of the functions we deal with for maximization on the continuous space we expect some concavity or regions of concavity if you're maximizing, or if you're minimizing, you expect regions of convexity. Right? So convexity and concavity are important, even if the function is not concave or convex everywhere. I hope that's clear. Concavity and convexity will always remain important, right? Only that regions you start looking at might be characterized by some initialization, or you may be able to show guarantee only within those regions. Okay, so we already provided. I provided you the notation and basics for vectors, matrices, and we'll look at implementing the loss function. So, yeah, this is a recap. We need strong linear algebra, matrix algebra here. So what will we do? We'll actually look at operational settings. A lot of it is operational settings through your projects. But to do that, we also need to make sure our mathematical understanding of smoothness, of strong convexity, right, of duality are all kind of primed up. So I will now talk about convexity as already motivated, and then talk about algorithms around it. It's going to be really fast paced like we've been doing so far. We'll also look at accelerated gradient descent, and this is something you cannot escape. You need to understand learning schedules, for example, why certain parameters are set the way they are, even while training large language models. And the schedules go wrong. I mean, Pratik, we had that experience yesterday. A schedule goes wrong, you have to basically restart. So why is that schedule so important, right? The learning rate schedules. And that a lot of it's based on accelerated, the notions of acceleration, which interplay between momentum and velocity, acceleration and velocity with respect to gradient descent. Some of them are also motivated by quasi-Newton approaches, which look at the Hessian, right? I don't know how much time we'll have. As always, we'll just maybe rushing through some of these. But this is what a wish list is. Yeah, we'll certainly talk about some modular functions when it comes to discrete optimization and some of the simple algorithms, right? But otherwise, this is again a very ideal wish list. Let's see how much we can do. We can't do theory and practice both, so we'll have to make a choice. So another way of looking at the continuous optimization problems, I mean, we'll have to start bucketing them differently, right? Because we want to be able to characterize their convexity, characterize their gradients. So we saw the supervised learning couple of losses, unsupervised learning couple of losses, but we see that contextual bandits are actually basically softmax estimators, right? I mean, we had a problem-based motivation, but now what you're looking at is a function-based description. These are all functional descriptions. Okay. So any doubts on the basics of continuous optimization? Anyone has? The notes I had shared last time. We'll take that, and then we had a homework problem also there, and then look at convex sets, right? So this is what I had set as your homework for today, 16 January, going through vectors, matrices, vector products, blah, blah, blah. All this was already posted. You're supposed to have done this, right? For example, if you have to look at Hessian of W1 square divided by W2. So you need to look at all the mixed partial derivatives. W1, W2, W1, W2, W1, which should be the same, and W1 twice differentiability with W1 and W2. Right? So let's consider the simple regularized logistic loss. Right? How did you compute the gradient of this loss? Did you try computing the gradient? It's very, very prototypical of most problems, right? So if this is just, as I said, this is a simple single variable. Okay, not a single variable. This is, yeah, the labels are -1 and +1, right? So how do you compute the gradient? Well, the first component is very simple. Right? You'll have a sum of all the Wi squares. So how do you visualize the gradients? So note that the function is scalar. I mean, a function is scalar valued, but the gradient is vector. Right. So basically, you'll have to say this is partial derivative of the loss with respect to W1 stacked again over partial derivatives with respect to W2 and W3 and so on. Right. So what we are trying to write down here is a vector form. Right. So you can think of this as the first component, which is partial derivative of W1 square with respect to W1 plus. So there's a plus everywhere, and that plus is basically a sum over those individual elements. Now, what this sum is needs a little bit more work to understand. But the first component of this vector is no brainer. It is basically a vector of W only, right? So this first component is only W's. This is a W vector basically. Sorry, there was a lambda by 2. So lambda by 2. And so because there's a lambda by 2, this just becomes lambda W. The first component is lambda W plus something. Okay. But the first component should be clear how you get. The second component requires you to identify that this exponentiated form is very interesting. When you take the gradient, this exponentiated form sticks around. Even with respect to the partial derivatives. So exponentiated form has a dot product between the W vector, but what will stay back, right, once you take the gradient is this exponentiated form divided by 1 plus the same exponentiated form, and what will come out are these xi's. Okay, so this plus part is going to have something with respect to the xi. Xi is a vector. Okay? Xi is the original feature vectors. What is this? This part, this is basically, I mean, very interestingly, it is minus yi divided by 1 plus the activation function kind of applied to W transpose xi. Okay, so there's no way we will be able to progress in the course if you don't do homework. So I have assumed that you have tried this out. In fact, I gave my homework problems were slightly more than this. Right, so this is okay. So we are going to actually compute the we'll look at all the homework problems, right? The solutions. This is one of them, right? So the partial derivative with respect to W is lambda W plus what I wrote on the board, right? Minus yi divided by. So there's a minus. I missed the minus. Yeah, there was a minus. Okay, now you can call this entire thing to be what? Sigma, right? This entire thing is sigma. And it turns out, so if sigma is basically 1 divided by 1 plus exp minus z. So when you write the Hessian, it turns out to be nothing but sigma into 1 minus sigma. Okay, that's very interesting about this entire form. And the Hessian will also involve the so-called outer product, xi transpose. Xi transpose is a rank 1 matrix. You remember? Xi is a column. By default, in this course, all vectors are column vectors. So xi into xi transpose should give you a rank 1 matrix. So this Hessian is basically a sum of weighted rank 1 matrices plus a lambda I. So why is this lambda I? Right, when I take the second derivative, you'll just have an identity, right? Lambda W, the first component, right? Okay, I mean I've reversed the order there on the board. The one on the blackboard and one on the slide are reversed in order. But I hope you got the idea. Okay, so this is I had asked you to try out all these, right? This was posted as a homework problem. All these combinations compute the gradient. So only gradient you could compute for the hinge loss SVM. That's not difficult at all, right? So here what you're trying to do is max of 0. So this is shown here, max of 0 and 1 minus yi W transpose xi. So moment you start looking at this max form, We will see later on there's something called a subgradient, which exists everywhere, right? But for us, we will only consider points for now where it is differentiable. So don't worry about where it is not differentiable. So yes, as I said, for convex functions, it's guaranteed that at points where it's not differentiable, you have something called a subdifferential. What I've showed in the gray region is a subdifferential. But when we talk about geometric interpretation, I will talk more about it. For now, how do you find the derivative? It's basically, if the max turns out to be 0, it's 0. If the max turns out to be 1 minus the other components, it's a negative of W of. Very simple, W into Y. Right? The perceptron update rule is just based on that. You all know the perceptron update rule, right? It just comes from finding its derivative when the max is at the second component. Okay. So, right. So any other discussion on the homework exercises? Any questions? If you have not attempted, you can also admit you have not. Any other questions? Do you want me to run through this again? Everyone is fine, and you have to be honest. Okay. Okay. So this these were the different. So least square loss is very simple. Right. Yeah. So this is what I showed there already, the gradient one. So one point, in case you need a little help, I've put this help slide as well. So moment you're looking at a complex form like this and you're trying to derive, just try and find one partial derivative. Okay. So in case you found it overwhelming looking at the entire vector, this is easy, right? Just find one partial derivative. What did I do here? So if you want, I'll just write this form and leave it at that. And we won't discuss any further on this. So what have I done here? I've said the partial derivative of this loss with respect to just one W. I think I've used Wj. So I have actually tried writing down this entire form. But before that, there's a chain rule, right? So chain rule, what I've tried to do is I have written the there's a partial derivative of the summation, which is minus j wj xij, the whole thing into yi for the ith instance. Okay, this is very easy. Minus xi yi. How do you now compose this into chain rule? That I have shown here. To find this partial derivative, I will take this part by chain rule and then sum over all the i's, right? So this, that's okay. I'll write this. So this is the inner part. This is the outer part by virtue of the chain rule, where I'll now sum over all the y's. This part, exp, the derivative is, there'll be a negative that comes out. And 1 plus exp, what will happen to log? You'll have 1 upon 1 plus, right? So that will come in the denominator. You see that? You have summation, then 1 plus exp of the whole thing. And in the numerator, you'll have this form, which is, yeah, I think that's it, right? Okay, there's a minus. There's just a minus here. Oh, that's part. Yeah, minus will come out of this. Is there anything else I missed out here? This is the correct form, right? Minus xij. Yeah. Oh, exp. I've missed one part, which is exp itself. Yeah, there's something missing here. This is exactly what I've written on the board. The chain rule invocation. Okay. Okay. The rest is all straightforward, right? Once you have the chain rule, I just substitute. The first part I didn't even do. Okay, the first part was lambda w. That part I didn't write. Lambda W plus. Okay. Yes. Hmm. Which expression? This one. This one? Here. Lambda W. No, there's a slight difference, right? Earlier there was a negative here. Okay. EXP of minus yi W transpose xi. Here my final expression, I've just said there's another way of writing it. Here the negative sign has disappeared. So basically what I've done is multiplied the numerator and denominator by EXP of yi into W transpose xij. A good question. There's no mistake. Okay. Hessian also is there, and I think I've just demystified even Hessian. How did he compute? Same thing, same principle. What I wrote down, I think you should just write. You have to get into the habit of writing. Otherwise, after a point, you'll be lost. So just write down. No, I won't do it now. You just write down this expression, the double derivative of L with respect to Wi and Wj. Okay, so like I did here, do the same exercise as your homework, or you should have done that, and that will give you exactly the form we showed earlier. Okay. Okay, so now we'll move on to convexity and motivation, and again leave with some homework problem. But why convexity? As I said, even if a function is non-convex, convergence is typically in terms of the convex regions of the function. But before we talk about convex functions, it's very interesting convex sets. In fact, convex sets are so foundational that there's a very strong connection between the convexity of a set and convexity of a function. You can't even define convex functions on non-convex sets for reasons that we'll see. But more importantly, there are some very interesting duality properties. The duality properties of convex functions are associated with their sets, with sets called epigraphs. Okay, so we'll begin with convex sets. So let's say look at this convex function, sorry, non-convex function. First thing is most deep learning models, they exhibit such losses, which are basically combinations of convex regions, right? So overall non-convex. But what is interesting is also that even if you are projecting, right, projected, when we take the example of projection for non-negative matrix factorization, we considered projection. The projection is also very inspired by convex algorithms for convex functions. Okay, and the projection also kind of implicitly assumes that there is some the region to which you're projecting is a convex set. Okay, so all you can imagine here what convex sets are, right? Take any 2 points in the set, the line segment joining those 2 points should be within the set. So projections are very naturally exploiting some convexity properties even in the set space. Okay, so for example, if you're looking at the trajectory, I want to make sure that the solution is in this convex, so-called convex. It doesn't look convex if I do it by hand, but it's a convex region, right? So the projection will again make use of the convexity of this region, and basically even for convex regions of functions, when you're looking at non-differentiability, then you look at subdifferentials or subgradients, which subdifferentials and subgradients emerge for non-differentiable convex functions, and they have a lot to gain from understanding convex sets again, okay, especially supporting hyperplane theorem and all that. So yeah, in fact, even the Frank-Wolf interior point methods, all of them do leverage convex set properties. So in fact, a course on convex, a typical course on convex optimizations, there's almost half a semester only on convex sets. Right? We won't do that here, but just to give you a flavor. And some of my earlier course on convex optimization, I would do that, go into great details on the theory part. Okay, and yeah, as I said, when you're looking at domains or constraints, like we saw already some of a constraints, right? The constraints are typically desirable to be convex sets. So this is exactly what I showed in the previous slide, but I'm showing the projection step in isolation from the overall optimization. Okay, so we will begin with convex sets and then move to convex functions very quickly. Convex sets, any two any 2 points, if you join them using a line segment, they should belong to the set. So is this convex set? By definition, no, right? And this is not convex because of this segment which comes around outside the set. Now it turns out that if you take any two convex sets, the intersection is convex, guaranteed to be convex, but the union need not be convex. So union of convex sets need not be convex. Projections are already motivated, but projection can be proved to be always unique if you are projecting to a convex set. Okay, this is just we will do more of the intuitive understanding on these questions in the class. So if I consider a point, so let's say a point X, okay, and the set is non-convex. What do you think? Understand by projection? Projection is basically some distance measured between the point and the set should be minimized. Do you think this can be unique always with a non-convex set? No, right? I mean, you can, especially if you're here. Let's say exactly here. You could have come here, you could have gone here. Projection need not be unique at all. But if the set were convex, the projection is guaranteed to be unique. So what are examples of convex sets, right? This is the projection, which makes it very useful for convex optimization. So this projection into convex sets, for example, this is very typical. I would project into a convex set, which is a ball, a disc, right? But it need not be a L2 ball. It could be an L1 ball, right? That's a very classic case of projection. So okay, I have this point here, and I need to project to this so-called L1 ball. Actually, this is that there are two kinds of balls here. What do you think is the difference between these two? These are balls under some norms. Which norm is used for the left-hand side and which is used for the right-hand side? Sorry? Which one is the infinity one? Left side. Okay, this is a norm ball. When I say norm of, sorry, this is not visible. Infinity norm of x is less than or equal to 1. Here, the one norm of x is less than or equal to 1. Okay. The other example is a hyperplane. So for half space, in this case, would also be half space. So I'm here, and I want to make sure that I'm on the positive quadrant. The positive quadrant is an example of half space, but you could also have a rotated half space, right? By the way, half spaces, hyperplanes are all relative, right? What appears to be a line in one dimension could be half space in some other dimension, or ray, for example, right? So it's all relative. From 3 dimensional, I slice, I get a 2-dimensional so-called hyperplane. But anything below that hyperplane is actually a half space in the 3 dimension. The other thing is, if you have a convex function, then the set, which is looking at all the function, the arguments where the function is upper bounded by a value k, right? This is called the sub-level set. The sub-level set fx less than or equal to k is a convex set. So yeah, I've tried to give examples, right? So union of convex sets need not be convex. Here's an example of 2 disjoint convex sets. Here I've tried to present examples of norm k less than or equal to norm x less than or equal to k. This is the one norm. You rightly identified that to be the one norm. The other one was the straight standing box, which is the infinity norm. Then we also show that, circle in xy plane, if you look at the projection, you expect it to be a unique projection. Yeah, and that I think these are some points. This is a hyperplane I was trying to explain earlier. Okay. Some more points. So now if I consider some set of arbitrary points and consider their convex combinations, if I consider all possible convex combinations, then you'll get a convex hull. Right? So if I've given all these points and if I consider bunch of all their convex combinations, then you get this hull. Likewise, earlier our set, this set was not convex, right? But if I consider this line segment and every line segment connecting any two pairs of points, then eventually even this gap will be filled up, right? So that filling up process gives you what you call the convex hull, right? So to have a convex hull, do you need S to be always convex? Not at all. You have a right. And what about the convexity of the convex hull itself? Is that guaranteed? By design, right? So one interesting thing here you can find with this specific example is, and this is a homework for you, right? Do you think you can characterize the notion of a supporting hyperplane? Right? A hyperplane that supports a set. A hyperplane such that the set is guaranteed to lie on one side while the hyperplane just touches the set, right? Or rather, it's tangential to the set. Now, intuitively looks like, right, that if it's a convex set, you should have a supporting hyperplane at every point. If it's not convex, if imagine this gap were not there, right? The gap were not filled up. Then I could not support it at arbitrary points. And this becomes easier to think about and meaningful to discuss when you consider convex hulls. So if I have considered this set, so I could consider a hyperplane here, but is there a supporting hyperplane here? A supporting hyperplane in this region? This entire region, once you fill up, then you have supporting hyperplanes. So give some thought to it. So is there a theorem? Do you think a theorem can be proved along these lines, right? Also, another mandatory homework is for you to verify, right? Please verify that if S is convex, then the convex hull of S is always convex. Okay, so I think the two homeworks I'm leaving for you. One is a little bit more exploratory homework of supporting hyperplanes. The other is to prove from first principles. Do that. Do the hard work by writing, and you will benefit, right? Yeah.
Every 2 points you draw and you lie with it. The convex hull of that set into the set itself.
Right. Convex hull of convex set is always the set itself. Will coincide. Convex hull of convex set will coincide with the set. Right. So this is the supporting hyperplane theorem. As I said, you need to read this a bit and understand. If you have two disjoint sets, C and B, so it's called a separating hyperplane. Sorry, the separating hyperplane theorem. The homework for you was to think about the supporting hyperplane theorem. So I'm giving you the separating hyperplane theorem to give you a lead into the solution, right? So if C and D are disjoint convex sets, right? Here I showed the example of so this is not convex, but this is a convex set C and D. If the disjoint convex sets, then there's guaranteed separating hyperplane between the two. And what does separating hyperplane mean? It means that the C A transpose X is going to be less than equal to B for all points in C and greater than equal to B for all points in D. Not necessarily a single hyperplane, there could be multiple such hyperplanes evident from this board, right? It's very intuitive. And of course, I'll point you to detailed proof of that I have provided in my earlier versions of the class. I have spent some time doing these proofs. Now, if you want to ensure that there is strict separation, what is strict separation? Means that they're disjoint, but no. Strict separation would mean that the hyperplane doesn't touch any of them. See, this is greater than equal to and less than equal to. Why do you think strict separation is not trivial? So strict separation requires that C is closed and D is singleton. If you have to prove it under all conditions. Why is it so difficult? I mean, why is it not so non-trivial? The answer is kind of there in the assumption. Open versus closed sets. That is a challenge, right? So you may have an open set C. You see what open set means? It doesn't contain its boundary, right? Open set C, and this is also an open set D. And what would be an example? I'll say x greater than 0, x less than 0. Okay, so or let's say, in fact, the other can be less, x greater than 0, x less than equal to 0. Is there a strict separation between these two? They are disjoint. X greater than 0 and x less than equal to 0 are disjoint. But is there a strict separation between these two? No. So if you want to prove it under all conditions, you'll need more work. But again, I'll not discuss this further. It's for you to think about. Okay. I have tried to give examples. If C is open and if boundary of C is not a subset of C, then there's a problem. That's what I've tried to show you. Like this is exactly the x greater than 0, x less than equal to 0 example. C is open, but boundary of C is not in C. Then you might have a problem in terms of strict separation. Yeah, and this is an example of strict separation here. C and D here are strictly separated on the figure here. Okay. Okay, then I think so this was a supporting hyperplane theorem. The interesting thing, this is a homework problem, but supporting hyperplane theorem can be proved based on the separating hyperplane theorem. That's the reason I left you with the separating hyperplane theorem. But this is your, how can you prove the supporting hyperplane theorem? If C is convex, then there exists a supporting hyperplane at every boundary point of C, where the supporting hyperplane basically means that at boundary point x naught, A transpose x is equal to A transpose x naught. But if at all other points, right, the C is exactly on one side, right? A transpose x is less than equal to A transpose x naught for all other points x and C. Okay, we'll stop here. Thanks.